Okay, couple of announcements before I move on. So, a couple of students send me emails about homework, so I just want to explain a few things. And then, of course, there was also feedback from the instructor evaluation forms. So, on the first day of class, I mentioned when I went over the syllabus. So, this is mentioned in the syllabus from the beginning of the quarter. And I'm also, I pointed it out on the first day of class, and I repeat it again. Homework assignments on Pearson, I have to have a due date to make them available to students. So I set a due date of June, which is like not even at the end of this quarter, is the end of spring quarter, right? At the end of the academic year. So that students have all assignments available to them at the beginning of the quarter. The point is that a lot of the material we cover at the beginning of this class is also covered in your prereq classes. Some professors don't like to actually spend a lot of time on the fundamental topics at the beginning because we expect students to retain the material. But I understand that it could have been, like a quarter or 2 quarters, even a year or longer since students might have taken physics 3 and 2. So it's hard to remember the material when you are not going to use it again. So I understand that. And that's the reason I spent some time at the beginning to go over some of the fundamental topics. When I go over the fundamental topics, actually in general, whenever we go over any topic, we assign homework because homework is an extension of your learning. You learn about some concepts in class, and then you would apply those concepts to homework. Some of them would be similar, some of them are not so much, because again, homework is an extension of your learning. It's not supposed to be exactly the same as the things that you learn in class. Right? In class, we only have an hour, actually less than an hour. So we cannot cover a lot of things. So homework is for that. It's an extension of your learning. So that was one point. One of the feedback says the homework does not accurately reflect what we do in class. Well, that's the reason. Homework is not supposed to be exactly the same as what you do in class. Okay. Some of it is going to be similar, but some of it is going to have expand on the concepts that we learn in class. So in class, for example, I talk about voltages and currents and how voltages are measured between 2 points. Then there's a homework problem which talks about voltages at 4 different points. And so it expands on the concept that we talk about in class. So that's one point. The other point is because the fundamental topics are covered, we do 1 or 2 topics on Monday. 2 days later, we do another 1 or 2 topics, and Friday again, we do 1 or 2 topics. At the beginning, these are small topics. And so the homework that is assigned to each particular topic also comes in a rush. We cover like 4 or 5 topics in 1 week. Well, then we have 4 or 5 homeworks right after the other. And that's the reason why. And then again, the important point that I started back at the beginning was homework is considered assigned once the topic is covered in class. Now, when I want to expand on that, topic is covered means when the beginning of the topic being introduced right to the end when we finish with the examples. Okay. So as an example, we talked about, let's say, let me bring up our slides. There we go. So for this section, we stopped at, where did we stop? Okay, we stopped at series parallel network analysis, right? We didn't get into voltage division. So voltage division for this section is not yet assigned, but I will we will introduce voltage division today, right? Actually, we went over voltage division. Well, that's good then. So we went over voltage division 2 days ago. So there is no reason for students to not be working on the homework. Okay, at least even look at it. So even if I didn't cover the example for voltage division and I had just covered the introductory material, meaning just explaining the derivation, I would expect students have to be responsible enough to actually open up the homework and take a look at it. Okay. Again, some topics might take more than one class to cover. Some topics might be split. Okay, we might cover the theory in one class and example in another class. But as soon as the topic is introduced, I expect students to open up that corresponding homework and start working on it. You might not be able to complete the entire homework, but there is no reason for students to not at least open it up and begin work. So again, As soon as the topic is introduced, students should open it up. And once the topic is covered in class, meaning when I'm done with the examples, students should expect that the homework is assigned. I will do a better job from now on to actually announcing in class itself, saying that, okay, topic is now covered, homework is assigned. But if the topic has been covered for more than 2 days, then those 2 days will count towards their due date. Okay. So voltage division was covered 2 days ago. I would expect students to actually cover, and some students actually have completed the voltage division problems that are available on the homework. And that is the point. The point of putting the homework assignments all out in advance is so that students can get a head start on it. And I think current division is remaining, right? So again, as an example, voltage division was covered. Current division will be covered today. Homework will be assigned. There are not a lot of problems in there. There are some for voltage and some for current division. But as soon as the topic is introduced in class, students should open up the corresponding homework. And when I complete the topic in class, when I finish covering the topic, I will announce in class, homework is assigned. The due date will be in a few days, so keep on top of it. Okay. And again, feedback has been good in the sense that I am receiving some positive comments. I'm receiving some negative comments in the sense that it's something that is not working for some students. So they send me an email about it. They send me feedback on the instructor evaluation form, and I'm able to address it in real time. So keep doing that. Okay. It's to all of our benefit. Okay. Any questions? Any questions at all? And yes, quiz solutions will be posted. I will open up. Typically, I open it up right after the quizzes are done. So pretty much on Monday afternoons. But Monday afternoons I have another lab, and so kind of got lost in the shuffle. But I will open up and I will post the quiz solutions as soon as class is over. Okay, let's continue with current division. So similar to voltage division, current division is also derived from Ohm's law. Oh, any questions from anyone? Online, in person? Anything about the homework assignments or about voltage division? Okay, moving on then. Current division is derived from Ohm's law, also derived from the series parallel analysis technique, where we take a large network of resistors and we reduce it down to one single resistance, find Req, and then apply Ohm's law again to find the voltage. So in this case, in current division, we have two parallel resistors, R1 and R2. We remove the source and find Req across the open terminals. And Req in this case would of course simply be the reciprocal of the sum of reciprocals of R1 and R2. Okay. Once you have Req, the circuit simply looks like this. One source and one resistance. Now, voltage V is of course given to us. It's a parallel network. So this is exactly the same node, and this is, at the bottom is also exactly the same node. There are only two nodes in any parallel circuit. Doesn't matter how many components are connected and how long the wire is, it's exactly the same junction point. Okay. And hence the voltage across the source and resistors R1 and R2 is exactly the same, which is V. So V in this case is simply IT times Req. IT times Req. Then I apply Ohm's law again. After expanding the circuit, I can write equation for I1 as V or R1. V in this case is IT times Req or R1. And that's it. Two-step derivation derived from Ohm's law and the series parallel analysis technique. It simply allows us to skip over a couple of steps. Okay. So when a current flows through a parallel circuit, it gets divided, and the division is in ratio of Req to that resistor itself. I1 is a fraction of IT. The fraction is given by Req divided by R1. Similarly, I2 is IT times Req over R2. That's it. It's a direct application. And students can have that equation on your equation sheets. It's just a tool for analysis. You can have all the tools you want on your equation sheet, but you should know how and when to use them. Okay. All right. Any questions? Again, in an exam or a quiz, if I ask you to solve it using current division or voltage division, please apply that equation directly. Even for this homework, do not take a shortcut. Do not try to apply Ohm's law and derive it that way. Okay, that defeats the purpose of the practice. Okay, for the homework, apply voltage division and apply current division directly and see whether you can solve it or not. If you take a shortcut and apply Ohm's law, again, you will not be getting that practice. Okay, let's see. All right, I'm getting a message. Current division was in the homework last night. That shouldn't be the case. If that was the case, I will extend the homework. Was current division due last night? Yeah, it shouldn't be, right? It shouldn't. 6 and 7. Did it have current division in there? It shouldn't, right? Yeah, number 8 should be voltage. So anyway, I'm receiving a comment which says current division was in the homework last night. It shouldn't be. Yeah, you can apply current division, but it's no. Anyway, so what was I saying? Oh, current division. Any questions? Yes. Yes. So that was going to be my next point. The 2 points to note about voltage as well as current division. So already marking here, I is the only current that flows through that circuit, right? So it's not possible for the current to take any other path. Current I remains the same in a series circuit, and voltage remains the same in a parallel circuit. Okay, so in a series circuit, current remains the same, but voltage gets divided. So voltage division is applied only to a series network of connections. And in current division, voltage remains the same. But current gets divided. Okay, as a reminder to online students, again, if you have a comment, please speak up. I am unable to actually lecture in person, broadcast on Zoom, and monitor the chat window. Okay, so monitoring the chat window is not feasible while I'm actually doing this. So if anyone has questions, please feel free to speak up. Okay, example of current division. We have 3 resistors here. One current source, IS is 15 amps, and parallel network gets divided, comes around, goes down I1, I2, and I3. So the first step is Let's isolate the current source. And we'll find Req for R1, R2, and R3. R2 and R3. In Req, in this case, is 1 over R1, 1 over R2, 1 over R3. So 1 over 10 plus 1 over 30 plus 1 over 60. This comes out to be 6.667 ohms. And now that we have Req, we apply current division to find I1. It's simply Is times Req divided by R1. Is 15. Req is 6.667 divided by 10. And this comes out to be 10 amps. By current division directly. I don't have a calculator in my head. This is just since I already did this for the 2 sections prior to this. That's why I remember the values. But again, you can take out your calculators and go along solving in class whenever I do an example. I2 would be Is times Req over R2. And I3 is Is times Req over R3. What is I2 and what is I3? Anyone? Wait. In I3. So look at the resistor values, then look at the current values. And you should be able to verify your answers at, well, at least approximate range. Okay, I'll wait. Let's take a 10-second pause while students write it down. Let me know if you have any questions. Any questions at all? Yes. Yes, you can do that. There's multiple ways to do it. There's multiple ways to do it. We can find voltages across, well, voltage is of course the same. We can find the voltage from Ohm's law. That's the series parallel analysis technique. But more important in this case, I was looking at the ratio of the resistors. It's a nice even ratio. So R3 is 6 times R1. R2 is 3 times R1. So resistance and current have the opposite relationship, inversely proportional to each other. The lower the resistance, the higher the current. So if R1 is 10 ohms and I get I1 as 10 amps, R2 is 3 times as much as R1. Correspondingly, I would expect I2 to be 1/3 of I1. So 10 amps, and I got 3.333, which is exactly 1/3. And then R3 is 6 times as much as R1. So I would expect I3 to be 1/6 or 1/6 of 10 amps. So 1.667. And that's what I was getting at. All right, any questions? Any questions at all? So next class is going to be on node voltage analysis and mesh current analysis. Okay, 2 important topics. We will apply what we have learned so far, KCL, KVL equations, applying those. And we'll begin with node voltages and mesh currents, identifying next class. So we'll end class here today. And we will pick up here on Wednesday. All right.
Professor?
Yes.
So I was looking at the homework 7. That one
Yes.
was due tonight, right? Or last night, I mean.
I don't have Pearson open in front of me here.
Okay, I
Or is
think
it
I
been due
do,
last night? Okay.
and it was due yesterday.
Okay.
And I was looking at some of these questions, and to me, it looks like it is current division.
Okay. Does it specifically ask for solving with current division?
Maybe not, but it does ask for I2 or I1 when it's like a portion of a parallel circuit. So I was a little bit confused how
If it
we
doesn't,
would know.
okay. I get what you're saying. As I said, circuits can be solved multiple ways. There are always multiple tools and methods to use. But if a question does not specifically ask for any specific method, then students are free to choose any method they want.
But I just don't even remember learning a method to do it with. So how do I choose if I don't know how to do it to begin with?
So it would be the series parallel analysis technique, where you reduce down to one single resistance, and then we expand it up, and then we apply Ohm's law, KCL, KVL, then multiple ways to solve for the same circuit.
Okay.
So there are no restrictions on which technique to apply. So when I went over the example, I specifically showed, I can't remember which one it was, but there was a problem where you could solve it using Ohm's law and we could solve it using KVL.
Okay.
And
So the one where you bring it all down to one equivalent resistor, how is that different from what we're doing right here? Because to me, it looks like we just brought it down to one equivalent resistor and then we're taking portions of it, just like
yes,
I would have done before.
so the derivation is from that series parallel analysis technique. So I mentioned that too. So the derivation for this, it comes from Ohm's law and series parallel analysis technique, where we reduce the circuit down to one REQ. But instead of finding the voltage and then finding the current, we simply skip one step and apply current division directly.
Okay, so the only difference between these two is that this one doesn't require the voltage.
Nope.
Okay.
That's if we skip one step. So at the beginning, I can rewind the video and go look at it, but I believe I did mention it.
I think you did mention it. I do agree. You
The
just didn't
advantage is just that it's,
write it
it
down.
allows us to skip one step.
Okay. It's to me they seem very, very similar.
It
And I
is
don't
derived. Yeah, it is derived, and it is similar. It is derived directly from series parallel analysis technique.
yeah, I just didn't remember us ever like writing it down on our notes like
Uh,
in class. So I had to look it up and I figured it out. I'm not worried about that. I was just curious, like for another topic, how would we know that like we should already know this if it wasn't like written in the notes or something like that?
No, what?
I don't remember us, well, I mean, I remember us talking about it, but it was never written in our notes how to do like division of current across parallels.
No, that's the topic that I just covered right now.
Yeah, I know that, but that was on the homework that was due last night.
As a problem?
Yes,
As a problem for credit, or are you talking about the extra
yes,
credit tutorials?
both. It was on both.
It shouldn't be. You send me an email and I'll take a look. If it's there, then I apologize and I will extend that, but it
It-
shouldn't be there.
I could be wrong too. Just that's how it looks like
Sure.
from how I solved it. So, I mean, you could solve it a different way than I just didn't realize, but that's how I solved it. So,
Okay. Well, as I said, I mean, if a question does not specifically ask for current division, then there is no point in saying that the question asks for it, right?
no, I'm just saying I don't know another way to solve it but current division. And I mean, it just says find the value. It doesn't tell me
Okay.
what way to solve it.
Okay.
So,
Send me an email so I can take a look at it closely, and if there's any error, I can rectify and I can answer better that way. Because
okay,
I
I
don't have
appreciate it.
Pearson on this class computer. This is like a lecture room computer, so I don't have Pearson on here.
Yeah, don't worry about it. I was just trying to figure out how I would know how to solve it because it doesn't
Okay.
say a specific
Okay.
way to solve it. So,
Okay. All right.
all right, thank you.
Mhm. Mhm. Yes. Yes. They should automatically be in. Hold on.